Hello there. In this video we're going to discuss how to numerically solve the diffusion equation, which is given by this expression. Ut is going to represent the partial derivative of u with respect to time, alpha is going to represent some diffusion constant, and the Laplacian of u is going to represent the sum of second order partial derivatives of u with respect to the spatial variables x, y, z, what have you. So in this video we're going to be primarily focusing on a finite difference method. We're not going to be discussing the stability of those methods, and we're also going to be simplifying this into the one-dimensional case for u. So this represents just the second order derivative of u with respect to x, which can be easily extended to higher dimensions if you desire. Alright, so let's begin by sketching out the finite difference method for the diffusion equation. So for the ut term, I'm just going to use a four-difference approximation for that. So this is going to be equal to u of t plus h. So t plus h. So I'm going to write my time variables in the exponents for simplicity of notation. So ut plus h minus u of t all over delta t. And that's going to be what this h is. So this is also going to be delta t. So that's going to be the approximation for ut. So then we're going to have approximately equal to alpha. And then we're going to use a finite difference method approximation for the second order partial derivative of u with respect to x. So that's going to be equal to, so this is going to be evaluated at time t. So this is going to be x plus h minus 2ut at x plus ut sub x minus h all over delta x. And that should be delta x, the quantity, squared. So for the general diffusion equation, sometimes there's a other term here, so I can call that, say, g of x of t, or whatever other variables you want to deal with. So I'm just going to throw that over there just in case you want to extend this to a more general diffusion equation. So I'm going to be solving for this equation for uxt plus delta t. So we're going to have u sub x raised to the power of t plus delta t. And that's going to be equal to, so we're going to add this uxt term. So u sub x to the power of t, not 5. Bad 5. And then we're going to have plus. So I'm going to be writing this as alpha delta t over delta x squared. So alpha delta t all over delta x, the quantity squared. So this is a constant multiplied by this term here on the top. Let's see if I can highlight that. Great. Save some time. And then we're going to have plus delta t times g. Alright, so this term here is going to be related if you want to do some stability analysis on this method. So I'm going to take this term and I'm going to define it to be some constant f. So f is going to be defined to be equal to alpha times delta t over delta x squared. Some people will call this the Fourier coefficient or the CFL, the Courant-Frederick-Lewis constant. I believe those are the names. But this is usually related to the stability of a finite difference method. But again, I'm not going to get into that. But I'm still going to define it as so. So this expression is going to be defined more simplistically as f times all this stuff. And keep in mind this is a function of gt, a function of t and x. So this expression here is my approximation for the diffusion equation for some arbitrary term at the end, g. So let's go into MATLAB and program this out. Alright, so we're going to begin by starting off with a blank script in MATLAB. We're not going to include the g function at the end of the general diffusion equation, so we're going to assume that g is equal to 0 for all t at all spatial values x. So the only other parameter value that we really need to take into consideration, so the diffusion parameters, is going to be alpha. So we're going to define that to be 0.5. And we're also going to construct our spatial dimension because we're going to have, say, a line from, say, x is equal to x0 to x is equal to xf. So let's construct our spatial domain. So xo I'm going to define to be the origin. Since we're only in one dimension, so we're pretty much looking at a subset of the real line. And xf is going to be whatever you want, 5. So the length of that interval is, of course, going to be equal to xf minus x0. So that's the length of the domain we're working with. And we're going to partition that into some small subintervals of size dx, or delta x, but there's no delta easily written here. So how many points are we going to have? So we're going to have n is equal to L divided by dx in this case. So that's the length of the interval divided by the number, the partition size. So that gives me the number of points. So my x domain, which I'm going to represent by a vector xdom, is going to start from x0 all the way down to dx all the way down to xf. So that's going to give me a vector with all of my x values located in them, starting at 0 and all the way going out to 5. So if I drop the semicolon after that and I display the value of x0, oh, what's f0? What is this? f0, this should be xf. So once I run that, you can actually look in the command prompt just to make sure it starts and ends where you want it to. So it starts off at 0, which is what I want, and it's going to end at 5, which is what we want also. So that's great. So my x domain is properly constructed, so I can semicolon that to suppress the output. So let us also construct a vector that is going to hold my solution components, and I'm going to call that u. So u I'm going to define to be equal to zeros of size 1, so 1 row since it's 1 dimension, and n plus 1 columns or values for which I'm going to store into it. Because if you have an interval with, say, 3 parts, say point here, point here, point here, there's 2 subintervals, but there's 3 points or n plus 1 points that are associated to it. So let's also talk about the initial condition. Since this is a PDE, we have a time variable, so there's going to be initial condition at t is equal to t initial. There's also going to be a boundary condition. So what is the boundary conditions on the boundaries of our spatial domain? How are they going to behave? So I'm going to define my u value, so u1, and this is what we call a vector operation, colon, so every single value is going to be equal to, and let's do a Gaussian shape for our initial condition, so e to the minus x squared. So x is going to be characterized by my vector, xdom, since that's my x domain. So each of these components in my x domain vector, I'm going to square each of those components, which is why I use the dot operator here. And those values are going to be assigned to their particular value in the solution domain. So if I graph this function, so if I plot, so if I do, say, figure, and then plot, and let's do xdom and u, and let's plot it in, say, blue circles or blue dots, or whatever style you want, then the graph of this should be, oh, what's going on here? Oh, here it is. Oh, that should be x0. I don't know why I didn't pick up that quicker. Alright, so once I get that, then I'm going to have this Gaussian here. Oh, I did a negative Gaussian. I guess it doesn't really matter, but usually we take a positive Gaussian as our unit shape. So we have a Gaussian, so that's going to be our initial condition. So as time changes, this curve is going to evolve through time. Alright, so that's pretty much what we're starting with here. So we don't really need this quite yet, so I'll just move that down. And let's start off with the boundary conditions. So boundary conditions. So maybe we're introducing some heat at a constant rate from particular positions on the boundary. So let's assume that the left boundary, so I'm going to represent that by LB, is going to be equal to 0.5. And the right boundary, let's assume that's like 0.7. So the first point of my solution, so first point is going to be u1, so 1 row, 1 dimension. The left point is going to be u11. That's going to be equal to the left boundary, and u1 n plus 1 is going to be the right boundary value. So this is the last point in the vector of u. And then, so if I plot that, So if I graph this, then you should be able to see here that the point at 0 is at 0.5 and the point at 5 is located at 0.7. So these curves should be approaching these values. So we're like putting a water that has a different temperature into this pool that has these particular heat sources or heat sinks, what have you, and this curve should diffuse towards this term and pretty much reach some equilibrium as time evolves to infinity. So that's pretty much what's going on here. So let's also talk about our temporal terms. So our temporal domain. So we're going to start our time at t is equal to 0, and we're going to end our time, t final, at say 100 seconds or milliseconds, depends on what units you're pretty much doing these things in. And delta t, I'm going to march through time at a space step of 0.01 seconds, or 1 millisecond if you may. Also, keep in mind, there was that constant, so other constants. I'm just going to call it a stability constant, because if you want to talk about stability analysis, you sort of need to understand this constant, and that's going to be alpha times dt divided by dx the quantity squared. All right, so that's going to be our stability constant. And before we get into our loop, so that's going to be, of course, for t is equal to t star all the way to t final, and step sizes of dt. We're going to start by letting u old to be equal to this initial condition for which I've constructed above. And of course, where's that graph at? So let's grab that thing. So we're going to assign it a figure number to be a little bit more cleaner. We have our x domain, and let's change this to u old. And let's graph that in a blue circle so it's a little bit more easier to see on the graph. And also let's do a grid. So grid on. Let's change our limits. So x limits on our graph is going to be equal to, let's do x0 minus dx to x final, what did I call it, xf, plus dx. So that's going to be our x domain. And our y limits, so this is going to be sort of deterministic on your actual values. So we're going from 0 to 1 since it's a Gaussian, and it's converging to limit points between these 2 points. So I'm going to go slightly below 0 and slightly above 1. So it's going to be, say, negative 0.1 and 1.1. I think that's appropriate limit values. So if I graph this to be a little bit more accurate, so this is my domain that I'm going to evolve over some time series, say t start to t final. Alright, so now let's start working on our for loop from t start to t final. Now let us assume you actually do not know what t final should be. If that is the case, then you might want to use a while loop here that pretty much continues on for an infinite amount of time until you actually stop the actual program. So those are just some things to keep in mind here. Alright, so we're going to begin by using that difference method that we talked about in the beginning video. So we're going to begin by talking about u mu. So first row, all columns except for the boundaries. So remember that our boundaries are located at values 1 and n plus 1. So we're only going to be changing the values from 2 to the number n. So this is going to be equal to u old. So we're going to be focusing on that interior portion from before. So u old from 1 to 2m. So 1 comma 2 to m. So that's the present value. So remember, that's the initial part. So this is the ut plus h term. This is the ut plus that stability constant times that interior parentheses term. So it's going to be u old 1. So we're going to be looking at the point in the future. So the point in the future of 2 is going to be 3. The point in the future of 5 is going to be 6. And the point in the future of n is going to be m plus 1. So we're going to take the vector and shift it to the right 1 unit. Then minus 2 times u old in the same exact position. So I'm going to go from 2 to m. And plus u old of 1 comma. Now the positions I'm going to look at here is the position to the left of it. So to the left of 2 is 1, to the left of n is n minus 1, so that's going to be the interval for which I'm going to be focusing on. So that's going to be the interior parentheses, and if you have that other term over here, that's going to be dt times that g function that we dealt with before. So that's going to be my finite difference method. So I'm going to make sure maybe you code this and you want to make sure that you haven't changed your boundaries. So I'm going to make sure u11 stays to be equal to ub. I'm going to make sure my other boundary u1n plus 1 is going to be rb, just to make sure those boundary conditions aren't changing by accident. That's just, just in case you're not familiar with coding. What I'm also going to do is I'm going to keep the initial state of my system drawn as well. So once I do that, what I'm going to do is I'm going to plot my x domain with respect to u. So u I haven't really changed and I'm never going to change it. So u is actually my initial condition. So I'm going to plot u and I'm going to plot it in dots to distinguish it from the other thing. And what I'm going to do is I'm going to hold that graph on to my new value. So I'm going to plot x domain, comma, my new values, and I'm going to plot it in, say, magenta circles. Now, I don't want to hold all these things on before, so before I get to this next step, I want to delete everything there. Then I'm going to plot it, hold on, plot that, and then when I get into my next iteration, delete what was there, plot my initial condition, plot my new condition, so I can sort of watch that evolution as time goes on. My x and y boundaries should be the same before I do the draw now animation. Let's also do the grid on and also then draw now once you have everything in there. And before we get into the next iteration, we need to update our things. So u old is going to be equal to u new, and that's going to continue from t start to t final. So let's make sure we have everything. What's wrong with this? U new? Oh, it changes on different sizes? Really? Huh. Well, it shouldn't change, so let's just say u new is equal to u old. I'm just going to overwrite that anyway, so that's actually not good. Okay, that makes it happy. So let's run this and see what happens. Alright, so nothing excited happened, so that's kind of sad. So let's try to figure out what's going on here. Alright, so let's actually take a moment to observe sort of what's going on here in this illustration. So let's run this again. So where's my graph at? So let's run this. So let's go, what's this nonsense? So yeah, it keeps on appearing on my other screen. So let's see if I can stop the animation briefly in the middle. So let's control. So if you actually look at the code, there are actually points that are coming up in this illustration, but there's a particular point where it sort of goes crazy. And I'm trying to stop it at a particular point here. All right, so here we have a graph where it pretty much shows that these values pretty much grow unbounded. So this is actually tied to the instability of the finite difference methods if this number f is too big. So if I actually zoom out and look at this value of f, so I get an f value of 50. So in order for the finite difference method to actually converge, the value of f actually has to be sufficiently small, and there's a necessary and sufficient condition for that. So what I'm actually going to do is I'm going to make dt a little bit more smaller so that my f value is a little bit more smaller. Now once you see that, you actually see that now my equation behaves very nicely. And again, I'm not going to get into what values of f make this actually true, but there is an actual value for some particular dt, dx, and alpha. So as we do see, our diffusion equation pretty much has our initial solution, which I'm graphing in blue, and it's pretty much converging to some curvature or some curve that connects the boundary points or the boundary values of this particular spatial domain. So let me just fast forward this to the future to sort of see what this converges to. Alright, so we waited a few minutes to sort of see how this would evolve, and it still has pretty much the general shape except this little, this convex region is a little bit more higher above what the initial condition was. But nonetheless, pretty much what this is going for is all the values pretty much converged downwards to this boundary value, and all these values down here are converging upwards to this value. And everything pretty much in between is going to slowly converge to some steady state solution in the middle. But we're not going to get into the theory of the diffusion equation and the exact curve for which it does converge to, which is of course an interesting problem to investigate. But this pretty much gives you a scenario of the diffusion equation and how to numerically solve it via finite difference methods. But of course, the finite difference method does come with a little thing that you have to keep in mind, is that this value of f has to be sufficiently small in order for it to converge. Else you sort of get something where the solution of u tends to get extremely large because the error pretty much propagates outwards and pretty much exponentially grows. But there's a really deep discussion, which is called von Neumann analysis, which you can actually investigate to sort of understand the stability of finite difference methods. But, we can discuss that at another time, of course. Hope you enjoyed.